All right, section 11.5, volume of pyramids and cones. You may recall last time we talked about volume of prisms and cylinders, where you really just find the area of the base and multiply it by the height. So depending on the shape, you might find the area of the base a different way. Well, today we're going to talk about building off of that and finding the volume. I think I said volume before, right? Volume of a pyramid and a cone. These two formulas for pyramids and cones are very similar to each other. Actually pretty similar to a prism and a cylinder as well. So let's just start off by talking about volume of a pyramid. And I'm not going to explain right now why this is, but the volume of the prism is, or a pyramid is just 1/3. 1/3 the product of the area of the base and the height. So the area, you still do the area of the base times the height, but it's 1/3 of that for both. This will be actually for both a pyramid and a cone. Pyramids, depending on the shape of the base, totally depends on how you'd find the area of the base. So you might think of a square. You just do one side, a square or rectangle. You just do length times width, or the for that base. If it's a regular polygon, though, you could do 1/2 the apothem times the perimeter. It just depends on the shape. So a couple examples for using this. Actually, just so you know, for pyramids, you might recall Cavalieri's principle last time. We talked about how if it's shaped weird, if it's an oblique, we call it an oblique shape. This would be an oblique pyramid, where the vertex is not right above, for a pyramid that is, not right above the center of the base. If it's off to a side, it's called oblique. So the height or the altitude is outside of the shape. It's still going to have the same volume as it would if it were inside, because you can find the height and you can still find the area of the base. So that does not change the way that the volume would be calculated. So a couple examples here. Example 1 we'll go ahead and do first. It does say find the volume of the pyramid, and we need to find the area of the base and multiply it by the height times 1/3. So that's our volume formula. So to find the area of the base, let's just look at length times width, because this is a square or a rectangular base. So the volume for this one will be 1/3. Area of the base is 8 times 5, which will be 40. And we're given the height, which is 10. And now it's just simple computations. So 1/3 times 40 times 10, or 1/3 of 400, which equals 133 1/3. So 133 1/3, or 0.33 repeating, centimeters cubed. Don't forget that when we're dealing with three-dimensional objects and the volume inside of a three-dimensional object, that is a cubed unit. All right, letter B. This is a square pyramid. They're both square pyramids, it looks like. Actually, no, the last one was a rectangle. This is a square pyramid, so we know both sides are 16 centimeters. Now, this time we're not given the height. We are, however, given a slant height. If the slant height is 10, we want to find the actual height, and we can make a right triangle here. It looks like right there, that would be a right triangle if you look at it. I mean, we can pull it out here. It would be a right triangle like this, and we're given this is 10. This is actually half. If it's a square pyramid, this would be half of 16, so this would have to be 8 down here. And we're just going to have to figure out what that height is then. So I'm going to use Pythagorean theorem. 8 squared plus b squared equals 10 squared. 64 equals plus b squared equals 100. Subtract that, we're going to get, I probably should have given myself some more room, but b squared is going to be equal to 36. Interesting. And so that height, even though it doesn't look like it from the picture, that height, when you take the square root of both sides, is going to be equal to 6. So we have the height of 6. All right? So if the height is 6, the volume would be 1/3. area of the base, which would be 16 times 16, 16 squared, times the height, which we said is 6. And I'm just going to use my calculator because that's what it's there for. So 16 times 16 times 6, and then 1/3 of that would make it 512 centimeters cubed. Alright, so that is volume of a pyramid. Let us look at the volume of a cone now. The volume of a cone is 1/3 the product of the area of the base times and the height. Weird, same thing. The only thing different about this is you find the area of a circle, because a cone has a circle base, different than a regular polygon. So 1/3 the base times the height, area of the base times the height, or in this case 1/3 pi r squared, because remember pi r squared is how you find the volume of a circle. Sorry, not the volume, the area, and then you multiply by the height as well. Let's look at a couple examples of that as well. Example 2, find the volume of these cones. So remember, volume, we just said it, 1/3 area of the base times the height, or pi r squared times the height. In this case, 1/3 times pi times the radius squared. So the radius is actually 2 if the diameter is 4. So times 2 squared. And the height is given as 5. Now we're going to leave these in exact terms. It doesn't say to, but we're going to leave it in exact terms. That makes it easier for us and makes it more precise. So 2 squared is 4, times 5 is 20, and 1/3 of 20 would be 6 2/3 pi meters cubed. All right? Or if you multiply that by pi to see what you end up getting, it's around 20.9 meters cubed. All right, second one. Letter B. Try this one on your own and see what you get. We're given the slant height. We're not given the actual height. So go ahead and find this one. All right, as I worked this one out, I found the height by using Pythagorean theorem. We have this radius. We have the slant height. We can find the actual height with the Pythagorean theorem. I got 8. I got 12 for the height. Plug that into the formula. 1/3 times pi r squared. So pi times 9 squared times the height of 12 gets you 324 pi, or it's going to be around 1,000, I think. Just 1,017.9 or so if you were to multiply that out. All right, we've got an oblique one here. Oblique's a little bit different, but not really. Remember we said Cavalier's principle means you still use the same formula, even if it's off to the side. Works the same way. So volume equals 1/3 times pi, because we have a cone again. It's just an oblique cone. The radius is even given, so 5 squared. The height is even given, and that would be times 9. And you end up getting an answer of, well, let me see, 75 pi, I believe. Because 1/3 of 9 is 3, multiply that by 25, 75 pi cube, centimeters cubed. All right, so oblique, don't let those fool you. They work the same way. Last question right now for cones. How does the volume of the above oblique cone compare to a right cone with the same radius and same height? And how do you know? How does the volume of the above oblique cone compare to a right cone with the same radius and the same height? How do you know? Well, they're the same. We just talked about it. Cavalier's principle. They're the same. As long as you have a cone, if we have the height, you have the radius, it's not going to change, even if it's an oblique cone. All right? Next time, we're going to actually talk about 2 examples of composite figures. If you can figure these out on your own, that would be fantastic. Just so you know, for this bottom one here, you can assume that this is a cube. So this is 13, and this is 13 as well. And you have enough information for the one on the right to find the volume as well. So composite figures, try to find the volume of the whole figure. But what I would like you to answer here is the 2 closing questions for sure. How do you know how to find the volume of a cone or pyramid or cone? how do the volumes of right solids compare to the volumes of oblique solids with the same dimensions? We kind of just talked about that. And then finally, if you'd like to try the error analysis ones, go ahead and try those as well. Find out where, specifically, maybe number one, the error is located. All right, that's it for section 11.5 for today on volume of pyramids and cones, and we'll see you next time.